Hi everyone, I'm Tianshuo, and in this video, I will talk about my paper CARDSHARK. The co-authors of the paper are Professor Gong Xiaorui and my advisor, Professor Liu Jian. In this work, we will discuss the triggering of concurrency bugs in the Linux kernel. This diagram here illustrates an abstract triggering process of a concurrency bug in the Linux kernel. Concurrency bugs are triggered when the racing syscalls run simultaneously and some events are executed in a specific order as marked by the red arrows. In this study, it doesn't matter what exactly the events are. They could be something like reading or writing to some certain variables. And the key takeaway here is that the chronological order of events are critical for the bug triggering. Concurrency bugs are known to be non-deterministic in their triggering. The basic method to trigger a concurrency bug involves using brute force by spawning two threads or processes to invoke the racing syscalls simultaneously, and this often requires multiple attempts. Although this non-determinism is well known, we actually know few about the reasons behind it. And in this study, we aim to fill the gap and answer the question why concurrency bugs are non-deterministic. And in this research, we identified a new factor named misalignment, and our study found that it's a dominant factor in the triggering process of concurrency bugs. In summary, the goal of our work is to understand the cause of this non-determinism, and based on our findings, we developed CARDSHARK to improve the triggerability of concurrency bugs. Our study focuses only on improving the triggerability, so we assume that the reproducers are already available, and we don't cover the exploitation of the bug's outcome, which are usually memory corruptions. The core of this study is a newly identified factor, misalignment. Let's first consider an ideal scenario where we assume that the racing point will always align within the time window when the racing syscalls are invoked at the same time. In this case, we will find that every attempt to trigger the bug will succeed, and concurrency bugs will be deterministic, just like non-concurrency bugs. However, this ideal alignment is based on our assumption and doesn't hold true in real-world scenarios. In real-world cases, it's actually very common that the racing point falls outside of the time window, and there to be a time difference between the racing point and the time window. In the following sections, we will explore how this occurs. When a syscall is invoked in the user space, the kernel serves it by executing some certain functions in the kernel space, which takes some time. This time is relatively stable and inherent to the syscall. So in concurrency bugs, the racing syscalls may take different time to reach their racing events from their invocation. For example, as shown in this diagram, the racing point might be at the start of the research pass, while the time window is in the very late stage of the receive pass. And this time difference can cause the racing point to fall outside of the time window. And we name this as the path disparity. Additionally, because of the nature of the scheduler, a thread or a process doesn't start executing right after its creation. The kernel will place a newly created thread in a queue for future scheduling. As a result, when the two waiting threads are created, there will be a random time difference in the actual timing of their execution. For instance, as illustrated in this diagram, the racing point might have completed before the other thread is scheduled. And this time difference can also cause the racing point to fall outside of the time window. And we refer to this time difference as the invocation disparity. So putting it together, we can see that the combined effect of path disparity and invocation disparity can cause the racing point to fall outside of the time window. And we formally define this combined effect as misalignment, which describes the time distance between the racing point and the center of the time window in one race attempt. For a race attempt to succeed, the racing point must align within the time window, but not necessarily the center of it, because the time window will remain open for a certain period of time. However, if the racing point is too far away from the time window center, it falls outside of it, and the attempt will fail. We formally describe this relationship between the misalignment and the time window length with this inequation. On the left side, we have misalignment, which is the combined effect of path disparity and invocation disparity, while the right side represents half of the time window length. This inequation expresses that if the misalignment is less than half of the time window length, the racing point falls within the time window, and when this holds, the race attempt will trigger the bug successfully. This inequation explains why a bug with a larger time window are more prone to triggering. It's because the time window length and the path disparity are inherent to the bug context, while the invocation disparity is a random value. So the larger time window can increase the likelihood for the inequation to hold. And this inequation also inspires our new technique, CARDSHARK. Existing methods like either fault FD, fuse, or explore race works by increasing the time window length, which is the right side of the inequation. However, we can also increase the likelihood for it to hold by decreasing the left side of it, which is the misalignment. And this is a core idea behind our technique, CARDSHARK. CARDSHARK decreases the misalignment with two steps. The first step is to synchronize the invocation timing of the racing syscalls. This synchronization can completely eliminate the invocation disparity. The second step is to introduce a delay to the invocation timing of one of the racing syscalls to offset the racing point within the time window. And that's essentially how CARDSHARK works. However, there is still one crucial question. This synchronization is simple, but how can we determine this delay? A straightforward approach is to marry it directly, which can be achieved through kernel instrumentation. We can record the past time of the racing syscall through instrumentation, and we can compute this delay by subtracting the two past times. However, this method is complex because to identify the instrumentation point in the kernel, we have to understand the root cause of the bug. So to make CARDSHARK more practical, we developed a technique called BlindShark. BlindShark can determine this align time without the needing to understand the root cause or instrument the kernel. It works by interleaving the two racing syscalls with all possible overlaps, and the concurrency bug will inevitably be triggered at a specific overlap. And when triggered, we can record the align time and reproduce it with CARDSHARK. Well, one thing to note about BlindShark is the align time found by BlindShark doesn't assure that the racing point aligns at the center of the time window, so it will be less effective. To evaluate the effectiveness of CARDSHARK, we collected 12 real-world concurrency bugs. We compared the average number of attempts and the time required to trigger each bug using CARDSHARK versus a brute force approach. As shown in the table, CARDSHARK can significantly improve the triggerability. And notably, CARDSHARK was even able to trigger 10 bugs with exactly one single attempt. And this was possible using the align time from kernel instrumentation. We also evaluated CARDSHARK using the align time from BlindShark. As shown in the table, it can still improve the triggerability a lot. And it is practical for real-world scenarios because we only need a reproducer and we don't need to understand the root cause or instrumenting the kernel. The prototype implementation of CARDSHARK and BlindShark, along with all the artifacts, are now open source at GitHub. And for any questions, you're welcome to reach me at this email address. Thank you for listening.